Right, let's start with the problem for the day. So I'll read this out. We consider the group with the set R difference minus 1 operation star, where A star B is equal to AB plus A plus B. Part A says show that this is an abelian group, and part B asks us to solve 3 star x equal to 15 based on the previous definition of star given in the question. So clearly, the solution for this problem lies in knowing the definition of a group, and more particularly what's an abelian group. Right, so let's look at a group. A group is always two things. That is a set and an operation. That is a group, simply. However, just having a set and an operation is not sufficient. There are conditions placed on the operation. There are 4 conditions in particular. The first one is closure. Closure is fairly simple. It says for the operands on which this operator operates, and this is a bit tricky, all the elements, if in the set G, the resulting element should also be in set G. So an example is 4 plus 3 are both real numbers, so the operation addition gives another real number 7. So since the operands of the operator plus are both real numbers, the operation's result is also a real number. This is all that closure is. I'll now express this more formally, and when we do that, it says for all elements, this used to represent for all, that belong to G, the result with the operation on those operands is also an element of G. That is closure. Fairly simple. Let's look at associativity. I hope I'm spelling it correctly. Associativity. Anyways, it's not an English class anyway. Let's look at an example here. Consider this, 3 plus 2 plus 4. I can evaluate this in many ways, but if I take this sum before, this becomes 5 plus 4. That gives me 9. There could have been another way of solving this where I'd taken this before, then it would have been 3 plus 6, it's still 9. You see how regardless of how you associated the addition, that is this operation, the result was the same. Such a thing is called associative. So you can say for all x, y, z in G, this is the same as this. That is, an association does not change the value, it is still maintained. It's a mathematical way of writing it. There's another thing, neutral element. Let's look at this now. This says that in this set G, for this operation, there's an element which returns the value. So let's look at addition again. You see how whenever you take any number and add 0 to it, it always gives the same number. This is the neutral element for addition in real number set. Another example, 4 into 1, 4. Again, there was an operation and 4 was retained. So 1 is the neutral element or identity element for the operation this. So this is expressed as there exists an element E. Sorry, this needs to be the other way around. This is called an existential quantifier. There needs to be an E in G such that for all elements that are in G, E operate, or you could go X operand E always gives X. This is a neutral element. Now what is an inverse element? Again, this is fairly obvious. An inverse element is the existence of an element I in G such that So in multiplication, 4 returns 1. This returns 1. So you see how in the context of multiplication, there's always an element that reduces the original operand to the identity element. 1 is the identity element for multiplication. So you say there exists an I in G such that for all x in G, xi just gives the identity element from here. This is the inverse element. This is all you need to prove to say that something is a group. That's all. So now let's do that. But before I just go on to that, let's look at what's an abelian group. An abelian group is still a group, but with just one more condition, that it must be commutative as well. Commutativity is simple. This means the order doesn't matter. So 3 plus 2 is the same as 2 plus 3. 4 times 3 is the same as 3 times 4. So it says for all x, y in G, this makes it commutative. And if it is closed, associative, neutral, inverse, commutative, it's called an abelian group. That's it. That's how simple it is. Okay, so now that we've done all the explanations, let's actually start proving it. Right, so I have already actually solved this. I'll refer to that as we solve this together. Let's prove closure. Let me take this out here. Yeah. Closure. Remember, if A, B are elements of the given set, this notation means all real numbers except minus 1. Then A star B is equal to AB plus A plus B. Something you must know is that the operation of multiplication and addition are closed already under the real number set. So all I really need to prove is that this will never produce minus 1 as long as any of these are not minus 1. Right? Maybe let me explain that better. You see how if you take 3 times 2 and these are real numbers, regardless of what kind of real number take a radical or a decimal or a fraction, anything, it always produces a real number. So this is multiplication is clearly closed, addition is closed in a similar way. So all I'll now prove is that this can never be minus 1, as that would be sufficient. Because I know this will be anything except that, any real number except that. Okay, so let's start by proving that. Minus 1. I must prove that this is not equal, but I'll start like this so that I can prove by contradiction. If I do this, I can go minus 1 is equal to A, B plus 1 plus B. I can take this here, minus 1 minus B is A, B plus 1. This is minus 1 minus B minus A, B plus 1. Clearly, this cancels this. A is minus 1. So, for this to entirely result in minus 1, either A needs to be minus 1 or B needs to be minus 1. But we've been given neither of them are minus 1. And therefore, I can say is closed. The operation star is closed under this domain. So proving closure was fairly straightforward, even though it requires to proceed with contradiction. All right, now let's move to the second thing, associativity. Proving associativity is usually just tedious. It's never really difficult per se, because it requires you to only follow along on both sides. So let's start with this. Let's first associate this. Let's see what that evaluates to. So that should be AB plus A plus B. This is based on the formula that gives you ABC plus AC plus BC plus ABC plus AC plus BC. Now let's look at a different association. If we do that, then it's A star BC plus B plus C. That goes right. So if we now do this, this should be ABC plus B plus C plus A plus BC plus B plus C. It needs to be ABC plus AB plus AC plus A BC plus B plus C. If you collect and compare these terms, actually this is not quite complete, I just realized. It's in fact not even, the C shouldn't be there. My bad. Yes, if you now compare and collect these terms, you'll find that these are actually equal, meaning that our operation is also associative. That is good. Now let's go for the third thing, neutral element. Right, so neutral element is finding something like E, which exists in the set, which just gives us A. So in this case, that must be something that looks like this. We just need to solve this. Let's solve this. So AE plus E is equal to 0. E can be taken common. A plus 1 is 0. And that just gives you E is equal to 0, which is an element of this, which is perfect. And since this is true, we know that there's a neutral element, and we can test this quickly. We can take something like 3 star 0, which is 3 times 0, plus 3 plus 0, which is just 3. So this does work. Let's talk about inverse right here. Inverse element requires you to prove A star I gives you E. We already found E to be 0. So you must find AI plus A plus I, which gives 0. Okay, let's take A common. That gives you I plus 1 plus I is equal to 0. Actually, it's better to solve for I first. So let's solve for that instead. So let's take I common instead. That gives you A plus 1 is equal to minus A. And I equals minus A plus 1. So this is how you can get an inverse element for any A. An interesting thing to note here is that this is not solvable when A is equal to minus 1, as this will evaluate to 0, the denominator. But that's okay, because we are not allowing minus 1 anyway. That's perfect. So we even found an inverse element. So we proved a neutral element and an inverse element. Now that we've proved the 4 things, we can say is a group now to prove that it's an abelian group, you must prove the 5th thing, commutative. Let's look at that. So let's go A star B is equal to AB plus A plus B, and B star A is equal to BA plus B plus A. Notice how these are algebraically equal, meaning is an abelian group. Simple. So that completes part A. Let's think about part B. That should be very quick. Let's go 3 star x is equal to 15. That shouldn't be too hard. We'll solve this. So that will give us 3x plus 3 plus x star x is equal to 15. That gives us 3x plus 3 plus x times x plus 3x plus 3 plus x plus x. This is really just fairly trivial, and it is highly algebraic, but yeah, it's doable. Nothing too difficult. We can now multiply everything, simplify to this. I already have this worked out, but for the sake of completeness, I'll write everything down. Which takes you to a quadratic equation. You can divide by 4 on both sides to make it a simpler thing, and then you can split the middle term and take common factors, which gives you x plus 3 minus 1 x plus 3 is equal to 0, and this gives you x plus 3 x minus 1 equal to 0, minus 2, and x is equal to 1. So it gives you two solutions, both of which are appropriate as they both belong to the set. And that solves the problem. That's it. Thank you.